Throughout this course on the chemistry of atoms, we have essentially assumed, certainly for chapters 1, 2, and 3, that atoms exist, atoms are a thing, the atomic theory of nature is a valid piece of bedrock for chemistry. And certainly this idea is consistent, or certainly doesn't contradict the results from chapters 1, 2, and 3. I mean, chapter 1 on the conservation of mass, certainly it makes sense that you can conceive of the conservation of mass as atoms not being able to be created or destroyed in any chemical reaction. In chapter 2, when we work to figure out the products of chemical reactions, magnesium and hydrochloric acid, for example, it made sense to sort of break down the equation into molecules and compounds, which themselves are made up of atoms. Again, the results we came up with didn't contradict the atomic theory. In chapter 3, when we broke apart water, when we electrocuted water, and out comes hydrogen and oxygen, again, the atomic theory of nature certainly does not certainly didn't contradict any results or meaning we found from that. And then we actually took a step back in chapter 4 and just kind of checked ourselves. So is the theory of atoms, and again, it's just such a fascinating piece of history. It was a raging debate throughout the 1800s. So in chapter 4, we kind of entered into that debate. We placed ourselves in the middle of that debate, ran a couple experiments, the effect of concentration on reaction rate and the effect of temperature on reaction rate. And again, not foolproof evidence that atoms exist, but certainly two additional experiments that don't contradict the theory of atoms. In fact, the theory of atoms nicely explains both experiments. So in chapter 5, let's take a deeper look, and let's actually try to prove once and for all that atoms exist. And if they do exist, they must have a mass. And so we're going to do these two things. We're going to prove that they are a thing, and we're going to try to prove that they are a thing, and we're going to go one step further and find the mass of one single atom. Now here's the catch. We're going to do this sort of metaphorically. We're going to run a model of an experiment. We're actually not going to do the experiment, and see if we could follow the logic of how scientists could find the mass of a single atom. And the logic is based off of one of the most elegant experiments in all of science. It's actually an experiment in physics done by Robert Millikan in Chicago in 1909. And it's called the Millikan oil drop experiment. Now what he did, he actually wasn't going after the mass of an atom. He was going after the charge of an electron, but also a very, very, very tiny number. You can't just pluck out an electron from somewhere and just say, okay, here's the value of the electric charge of one electron. But his logic was to suspend many little droplets of oil in midair, sort of suspended with an electric field. And he was able to measure the charge on these many drops of oil droplets. And what he realized was the charge of every single oil droplet were all multiples of some number. And then he just employed logic and was like, that number is probably the charge of a single electron. So your job, your challenge is to see if you can take the logic that Millikan used in finding the charge of a single electron to see if you can find the mass of one bead amongst many piles of beads. And so if you mass many piles of beads, and the value of the mass of these different piles of beads are all multiples of some number, then that some number could be the mass of a single bead. Sort of just using more mathematical language, what you want to do is find the least common factor of a set of numbers. That least common factor could be the mass of a single atom.